Hi and welcome back to another lesson in the physics video series. Today we will be discussing centripetal force examples, in particular constant speed with a changing radius. Let's take a look at what happens when we go from a wide turn through a tight turn through a sharp turn and see the changes that are produced in the centripetal acceleration and the centripetal force respectively. Okay, let's get started. As we introduced, we're going to take a look at what happens to the centripetal force and centripetal acceleration as we vary the radius. Let's make the mass of the car 1,000 kilograms and its speed around the circle 10 meters per second. I've chosen a point on the circle to help you understand the direction of the centripetal force vector, the acceleration vector, and the tangential velocity vector. I've also drawn them out for you on the circle in such a way that we can apply this hand gesture so that you'll never forget which way these vectors point. So what I've done is taken a picture of my hand and I've placed on top of it the red arrow along the middle finger for the centripetal force, the blue arrow along the pointer finger for the centripetal acceleration, and the green arrow pointing at 90 degrees to both of those along the thumb. At any point you can place your hand in this gesture on the circle and you'll always know that the centripetal force and acceleration are parallel to each other and the tangential velocity is always at 90 degrees to the blue and red vectors. If the object is circulating counterclockwise, as it is here, you'll see that the V-tan will follow the circle in this direction. But if the mass was circulating in a clockwise direction, this V-tan arrow would be pointing down in the opposite direction. Recall that we're going to be using equations 17 and 18 to solve this problem. And don't forget that we will also be using the V-tan equation, 2 pi r circumference divided by period around. This is no longer on the reference table, but I put it here for your convenience. To find the centripetal acceleration, we're going to use the formula v squared over r. And since we know that the v will remain constant at 10 meters per second, but only the radius will change from 40 meters to 20 meters down to 10 meters, we will change that radius in the problem. So this is a constant speed changing radius problem. I've taken 40 meters as the starting radius, and then I will cut that in half down to 20, then I will cut the 20 down in half to 10. So we will look at a wide turn, a tight turn, and a sharp turn, and we will see what happens to the centripetal acceleration. 10 meters per second squared over 40 meters gives you 2.5 meter per second squared acceleration pointing towards the center. However, if I change the radius from 40 to 20, so I take half of this radius, I wind up doubling the answer. 2.5 jumps up to 5 meters per second squared. And here's the math, 10 squared over 20 meters. And then, of course, if I cut this in half again, I wound up doubling the answer again. But here's the math, 10 squared over 10. Get 10 meters per second squared acceleration. So you could see a general trend here. And the trend is this. As I halve the radius, I double the acceleration. Halve the radius again, double the acceleration again. This is a very important relationship because you can see that acceleration and radius are inverse proportional. Now let's take a look at what happens to the centripetal force required to keep the car on that turn as the radius decreases from wide to sharp. We know that the centripetal force is equal to Fc equals MAC. F equals ma, also mv squared over r. Since we did the calculation for mv squared over r above, and we got the values for centripetal acceleration right here, a sub c equals 2.5 meters per second squared, we multiply that by the mass of the car, 1,000 kilograms, times the 2.5 meters per second squared, gives you 2,500 newtons. We know also that as we halved the radius, we wound up doubling the acceleration, and therefore you can see the multiplication of that new acceleration times the original mass of the car now gives you 5,000 newtons, which is double the force. So there is a direct relationship between the force and the acceleration. If you half the radius, you double the acceleration, and you also double the force. And here it is one last time. We have a 10 meter per second squared acceleration. We multiply that by the original 1,000 kilograms, and now we have a 10,000 Newton force. And so we can make a general observation. The larger the radius it has going around, the less force is required to keep it in the circle. And similarly, the smaller the radius it has going around, the more force is required to keep it in a circle. And finally, let's take a look at the relationships in the actual expressions. F equals mv squared over r. So if we held all things constant except for speed, then radius, then mass, we can take a look at the relationship between the force and a variation in that particular variable. So in the case of velocity, F to v ratio, a power of 1 to power of 2. So it is a squared relationship. That's a parabola. However, F to r, holding all things constant, r is raised to the first power. It's really 1 over r. That's an inverse relationship. And of course, F to m. Here's the mass. Mass is to the first power, and it's in the numerator, so it is a linear relationship. So what does this mean? If I was to double the velocity, then I would actually double and square it, which gives me quadruple. I would have 4 times required centripetal force. However, if I was to double the distance, 1 over 2, I would halve the required force. If I was to double the mass, then I would double the force required to keep it in a circle. Here we'll look at the other expression, F equals 4 pi squared mr over t squared, and we're really concerned here about the time it takes to go around. This is a 1 over t squared. This is an inverse squared relationship. If I double the time it takes to go around, 2 squared is 4, 1/4 of the force that is required. But if I halve the time it takes to go around, it means I go around more quickly. So that's 1 over 1/2 squared, which is 1 over 1/4. Inverse that, you get quadruple. As a car goes around a curve, the driver can only really change his speed. He can't change the mass of the car, and he certainly can't control the radius at which the car is turning. So we could see that for a tight turn, a car that's going too fast is going to fly off the curve, because as the radius decreases, the required force increases. So the best way for the driver to handle that situation is to decrease his speed. A cut of 1/2 of his original speed will cause a quartering of the force required to keep him on the road. These are some of the intuitive skills that new drivers lack, and they hit turns too quickly. Hence the name Dead Man's Curve in places where the road suddenly becomes a sharp turn. An experienced driver would foresee this and would go through the turn more slowly, requiring less centripetal force and a safe ride for everyone. I hope you enjoyed this video, and I thank you for watching. In the next video, we're going to cover the changing speed with a constant radius and see the different effects that has on handling a curve. We'll see you there.